Hello everybody, I'm your host Helwig, and I'd like to welcome you to The Space Industry by satsearch, where we share stories about the companies taking us into orbit. In this podcast, we delve into the opinions and expertise of the people behind the commercial space organisations of today who could become the household names of tomorrow. Before we get started with the episode, remember you can find out more information about the suppliers, products and innovations that are mentioned in this discussion on the global marketplace for space at satsearch.com. Hello there and welcome to today's episode of the Space Industry Podcast by satsearch. I'm joined today by some returning guests on the podcast, Michael Seidl and Adrian Helwig from global electronics manufacturer and satsearch trusted supplier, Texas Instruments, a name you just must be familiar with if you've listened to this podcast, but also if you're anything to do with the space industry or a wide range of other industries where Texas Instruments, or TI as it's commonly known, operates. It's great to have you both back on the show. Really interested to hear more about the work that TI is doing in space. There's always a lot of information presented by the company about the different applications and components and how they can be used to improve missions that TI shares. So this is great. Now, today, we're going to be talking about phased array antennas and how they can improve both performance and flexibility, or versatility, which is increasingly important in modern space missions, as we're seeing teams professionalizing and services trying to get more value and do more with the equipment and the resources and the people that they have. Yeah, really excited to get into this topic today. Now, we'll start by setting the scene a little bit. Many people in the space industry are increasingly aware of how congested the RF spectrum has become and is becoming. And there's a few different reasons for this. I wondered if Adrian potentially could explain why this problem has come about and what RF engineers are doing or can do to mitigate it.
Yes, sure. Welcome, everybody. Yeah, so I will be happy to answer that one. So the RF spectrum has become very crowded for several reasons, really. And the fact is, we need more data and faster speeds, right? So the demand for available spectrum simply has increased. In addition to that, there are also many new applications in services, like, for example, phone services, internet services, or Earth observation satellites, like weather satellites, for example, defense communication. And those applications are using up more of the spectrum. And let me also add one additional point here about the low Earth orbit satellites. Because on the one hand, you can think those are offering more data transmission opportunities for your system. But at the same time, they are also creating another problem, right? Because those satellites are moving very quickly relative to ground. And this makes really hard to maintain the stable communication link. Yeah. And now to deal with all those issues, engineers, developers, they are developing new solutions. And to be very honest with you, the one of most promising is the use of phased array antennas. So actually our topic today. And these antennas can direct the communication beam electronically without needing mechanical parts to move. And this allows really for better use of available spectrum by sending multiple signals at different angles and frequencies. And at the same time, this technology helps also to reduce the interference and improves overall system efficiency in using the RF spectrum. So, in summary, by using the phased array antennas, the space industry can really benefit and handle the anyway very crowded RF spectrum much better.
Okay, fantastic. Yeah, it makes sense as we've seen the industry scaling that this very valuable areas of the spectrum are under increasing demand. But yeah, when you explain issues like the LEO satellites, the how hard it is to maintain those stable communication links, I think that really puts this issue into perspective. And as you say, the phased array antenna technology is seen as a really promising solution for this. As I mentioned in the intro to the show, let's get into more detail on this technology. Now, as far as I understand, phased array antennas bring two big benefits: the increased versatility because of as you mentioned, the digital beamforming or the electronic steering, and that I believe they can enable greater bandwidth because they can operate with narrower beams. So I wondered if we could discuss this first point, and please correct my inaccuracies if they are there. But yeah, I wondered if Michael, if you could explain what digital beamforming is and what benefits it can bring to space applications.
Yes, very happy to attempt. This is definitely not trivial to understand, but let me give it a try. Imagine you have several antennas, not only one antenna, but you have several antennas next to each other, and you really put them equally spaced, one next to the other, right? And they form an array of antenna that's either a linear array in only one dimension that they're next to each other, or you put them in a rectangular format and have them in two dimensions spaced next to each other. But you have multiple antennas, and all these antennas, they send the very same signal, right? They just add up, they accumulate and form altogether a radiation characteristic with a single beam, but a more focused beam than if you have only a single element. So that's the first thing we have to put there to get a more narrow, more focused beam, because you're accumulating the characteristics of multiple antennas together. And the second one, and that's actually a pretty interesting, even fascinating fact happening there. What people do now is they put a delay where you're saying all antenna elements send the same signal. They do send the same signal, but each one a little bit later than the other one. So you put this constant delay on each one of those next to each other. And then the interesting thing, what happens then, is then the angle of radiation changes its direction, like the wave front is moving in a different direction then, and really controllable by the delay you apply to each of these elements. And that makes now this antenna steered purely based on electronics, so no mechanics involved. And that is, of course, a big benefit, that if you don't have to send many mechanics to space, that is, of course, a major advantage. And now the next level of interest is like you can have this steering of the beam you're radiating. You can differentiate between frequencies. So you have one carrier frequency getting one set of delays, and the other carrier frequency getting a different set of delays. And with that, you have now two beams of different frequency pointing at different locations. And this is where you can now put groups on ground, user groups on ground together, and give this one group one carrier frequency in one direction, and the other group another carrier frequency. And this is how you divide up the spectrum very effectively and with a very focused beam, where you accomplish then the best signal to noise ratio on these user groups.
Really interesting. So it's almost as if you're operating with two different antennas physically pointing in two different directions, but you aren't. You're using the same one that's electronically pointing the beam in different directions. Interesting. And then what about the achieving the increased data rate by operating with narrow beams? How does this aspect of things work?
Yeah, so that's really another aspect of using those phased array antennas. Let me try to explain. Achieving those increased data rates by operating with narrow beams works because these better focused antenna beams ensure that the transmitted signal arrives at the receiver with greater strength. And when the signal is stronger, it improves so-called signal-to-noise ratio, right? And this means there is less interference and the received signal is clearer. And this clearer signal allows simply for higher data throughput, as more information can be transmitted accurately and efficiently. So thinking about this, those narrow beams are really essential in boosting data rates and making the communication link more reliable and robust.
I see. That makes sense. Crucial. Okay, yeah, got it. So we have this technology, the phased array antenna technology. It provides these certain benefits around increasing the data rate and so on. Now, Oh, and we mentioned that the RF spectrum is getting particularly crowded, therefore this kind of technology is needed. But to bring it to home so that space engineers and mission designers really understand what value this technology brings, I wondered if you could give some examples of different space applications and services that would benefit the most from using phased array antenna technology, and why that would be the case.
Yeah. So there are really many, and I can try to list some of them. In general, phased array antennas would really greatly benefit and would greatly benefit any space application that relies on high data transmission, right? So the best example here is telecommunication services. Why? Yeah, because they need high data rates. Another example could be radar imaging applications. Those applications would also benefit from this because they need very strong focused beams for accurate imaging. And there is also another aspect I wanted to talk here. Those more focused beams helps also to reduce the transmit power, right? And this makes the whole system much more efficient. And now, at the beginning, we were talking about the challenges of low Earth orbit satellites and their rapid movement relative to ground. So now, with the phased array antennas, they can quickly adjust to compensate for those rapid movements. And this ensure again the reliable communication link, right? So overall, those phased array antennas improve your performance, your efficiency, and reliability across really a wide range of space applications and services.
Okay, makes sense. But of course, we always try and address this when we talk about space engineering. Missions in space are all about compromise. And as you mentioned earlier, we can't send mechanics into space to fix things. There are unique limitations placed upon any technology because of the extremes of the operating environment. So, my next question is, how is the swap C budget of a mission affected by using phased array antennas? And what can engineers do to deal with the, I would guess, inevitable trade offs that would occur by using these technologies?
Yeah. Yeah, I think first off, I think you suspected already, looking at the number of elements, the amount of electronics and the cost and the power budget and the size and the weight all goes up. So your swap or the size, weight, and power and cost budget is at the first glance compromised. But what you get in return is, of course, the amount of data rate and the amount of data rate per user you accomplish with it. And that really matters, right? And this is where the ratio improves a lot, right? So it's absolutely worthwhile going there in this direction by increasing the data rate. And we said it before, right? No need for mechanical steering is, of course, also a very good benefit, important benefit. And it's super fast, right? As we move over ground very fast, that is where these electronically steered antennas help us very much with. The big challenge that is probably will always be around with us, we put a lot of electronics in a very dense area, and that is where the challenge is. And of course, the amount of electronics and the complexity increases the cost. But this is where the good news is that meanwhile, the electronics industry and semiconductor industry has come up with solutions that really make it now possible to come at reasonable heat development and reasonable cost, so we can really enable these phased array antennas now also for satellite missions.
Fantastic. Yeah, thanks for addressing the balance that needs to be struck. The heat generation is one thing, but as we're seeing something of a trend towards larger form factor systems in the industry, this is partially mitigated because obviously larger systems are able to deal with heat generation, waste heat in different ways. And also then you can cope with more complex engineering sometimes more easily in a larger system. Excuse me. But yeah, the balance that needs to be struck in terms of increasing the swap budget is key. And as you highlighted, Michael, the aim is to get a great balance of cost for performance, not absolute cost. So yeah, if the cost at which you're developing data, generating data, is lower and the data quality is higher based on the same unit, then you're in a good position. But you also highlighted the complexity involved in the engineering here. As a provider of these sort of systems, how does Texas Instruments help engineers, or how can you help engineers to deal with this complexity and incorporate phased array antennas into designs and development of space missions?
Yeah, so we are really offering a wide range of solutions here to help engineers to use this technology in their designs. Let me talk about some of them. Obviously, we need to start with high-speed ADCs, DUCs, and analog front ends, all right? And TI is offering really advanced ADCs and DUCs with high data rates and wide bandwidths at the same time with lower power consumption and lower noise. You need those data converters for capturing and transmitting, and to be honest, sometimes even for processing the high frequency signals accurately. And I'm thinking here about devices like the ADC 12DJ 5200-SP for receiving part, but also on the transmit part, for example, the DAC 39 RF10-SP can be used. Now, if the customers prefer more integrated solution, we can also offer so-called analog frontends. Those products simply integrate several of those ADCs and DUCs into one device. And I'm thinking here especially about the recently released AFE 7950-SP, which is our direct sampling analog frontend, which supports frequencies up to X-band. Now, if you talk about ADCs and DUCs, obviously you also need to consider clocking, which is also essential for those kind of applications, because you need extremely low phase noise and jitter, sometimes even to femtoseconds level, right? And another important topic when talking about clocking is the synchronization feature with very high accuracy, sometimes down to 1 picoseconds. And this is really essential for maintaining this precise timing between phased array systems and elements. And now, if the customers needs jitter cleaning and distribution capabilities for clocking signals, they can use our LMK 04832-SP. Or if they, for example, need to generate a signal and need a synthesizer, they can use LMX2615-SP or the LMX2694-SP. In addition to that, I also wanted to mention a pretty new trend also in space application. A lot of customers already trying to replace their bulky discrete balloons with fully differential amplifiers. And exactly for that reason, we are offering products with high linearity across a wide bandwidth, up to 12 gigahertz at the moment. And the current portfolio supports 1 dB gain flatness up to around 8 gigahertz at the moment. The product is called TRF0206SP, which is exactly fully differential amplifiers for this kind of application. And now the big advantage, this fully differential amplifier compared to the balloon is much smaller and much lighter. So that's a really perfect fit for those space constraints applications like communication equipment, for example.
Okay, yeah, I see. You guys are clearly thinking about everything required to really incorporate the phased array antenna technology into space mission designs and deal with the interfaces and the data rates, managing the data rates and getting the best out of those systems and your communication system as a whole. What about the power management, however? How is this dealt with?
Yeah, this is, of course, also a super important topic, especially on phased array antennas. And the one thing is you need to have these power distribution or power generation devices a very highly efficient in a small form factor. So we talk about power density very high, and we're talking RF solutions. So we need to also have very low noise, right? We're highly interested in the signal performance. Cannot use any noise there, and so there is quite a lot of solutions we can offer here to really provide here a very accurate and stable power supply. So here's the so-called point of loads, the POLs, like the TPS7H4011-SP that allows you even up to a 12-volt input to generate the low voltages. Or you have another good example is an LDO, a very low noise LDO is called the TPS7H1111-SP, very easy to remember. That has such low noise or high PSRR, the power supply rejection ratio is so extremely good on that one that customers call it really, it's like this is an ideal power supply for us. And that is, of course, extremely helpful for the end product, of course, but also during development. As you optimize the system, you just know there's one thing less to worry about. You have a perfect rail. Whatever causes your signal to degrade, it's not that power rail. That makes things a lot easier for you, of course. So that's the overall power tree for supplying the data converters and maybe the FPGA and processing capabilities. Another key element in the power budget is, of course, the power amplifier. The power you transmit has to be all generated by this power amplifier. And these solid state power amplifiers, modern devices, they need a very complex biasing control system. So they need a certain voltage level that needs to be supplied. And according to the temperature and the current running through the power amplifier, you need to adjust this biasing voltage. And here comes a device from TI that is very helpful here. It's called an AFE 11612-SEP, a highly integrated analog front end that has 12 DACs and 16 ADCs, plus temperature sensors and a couple of GPIOs integrated. And that really helps to get here the PA biasing and control implemented in a very effective way. That's the aspect of the power tree itself, but in space, we have also the topic, and this was many times not really immediately thought about, is the fault detection, isolation, and recovery. So whatever we do in space, we need to make sure if something goes wrong, the electronics quickly identify the problem, but not only identify it, but they need to isolate the problem from the rest of the system and need to see how to recover from that and get the system back up working. So this fault detection, isolation, and recovery is a play of where you need to, of course, need sensors and detect the problem. So we have this in our power devices, oftentimes integrated with the overcurrent protection, over voltage protection and detection, over temperature detection, and corresponding fault output pin. So the system can be informed that something went wrong. As we talk about isolation, we have load switches even with precision current sensing implemented meanwhile. Like here's a device like the TPS7H2140-SP. So this is a 32 volt quad channel eFuse. And these load switches can then either automatically detect that something is wrong and switch off and isolate the problematic system from the rest of the bus, or can be actually be controlled by another system manager to disconnect things. And this control and management, or orchestrating this whole fault detection, isolation, and recovery, there comes a device handy. It's called the TMS570LC4357-SEP. It's an MCU we just released for space grade. It's a device integrating our Cortex R5 floating point cores, and actually two of them are operating in lockstep. And this overall design here being especially developed for high reliability applications, that offers really a very high diagnostic coverage, but also a very near instant fault detection, as we call it, and is here very helpful in orchestrate the FDIR.
Michael, let me add maybe additional point also on the multi-mission support, right? Because it's also a very important point. And TI supports simply different mission requirements also. So depending on the orbit customer is operating the application, so low Earth orbit or geostationary orbit, the customers can choose between a plastic package with higher radiation performance, so-called QML class P, or plastic space enhanced product, so-called SEP. And now the most important advantage, those products are in most cases pin-to-pin compatible, which offers a huge flexibility for customers in their designs. And at the same time, it makes sure, customers are using dedicated product for their space environment.
Okay, yeah, this is a very important aspect as well, as we're seeing, as we discussed, more versatile missions, longer missions, or missions with multiple goals that may be in different orbits potentially, or a customer who's creating technology for different satellites or different vehicles, whatever it is, for different orbits that, but they want to limit non-recurring energy by non-recurring engineering, apologies, with a consistent aspect of the technology. So yeah, this is great. Thank you. So I can see how much that TI is doing in this area, and mentioning fault detection and understand the power management separately from the data rates and the data chain compatibility has been really useful. Thank you. Thank you for going into detail on this. And to the listeners, we'll obviously share more information about the different products and TI resources that have been mentioned in the show notes. So you can read more into how these sorts of technologies and the designs, the application notes and the thinking behind them can be readily incorporated into your designs, your plans, if this is of interest to you. So thank you guys for that. I just wanted to wrap up by, coming back to the topic that we started with and discuss how, in a wider sense, you see this aspect of the space industry evolving. It would seem like the RF spectrum is only going to become more crowded in the short term. And we might then run into issues with an increased regulatory burden, with the bodies in charge of apportioning and controlling the spectrum are requiring a greater admin overhead of space missions and companies, and might even make it difficult for some companies, especially those smaller, newer teams, to get satellites into orbit on timescales and budgets that make sense to them. Yeah, I wondered what your thoughts were on how you see this area changing and progressing, moving forwards.
Yeah, I think it's definitely on the move, and I think we have reached critical mass. So that's the trend to phased array antennas is probably very hard to reverse anymore. But what we will definitely see moving forward is that we will see an increase of number of elements, because that gives you always, as we talked about before, a more focused beam that you want, and allows you also have even more beams per antenna. And that all translates then into those benefits of you have maybe more users and higher data rates per user, per beam, more users overall. So just a bigger business after all. The other trend, as you say, that spectrum is getting crowded. So people try to go even higher frequency bands. And as technology proceeds, where this is entirely possible, and here comes for a change something good. The higher you go in frequency, you're shrinking the space needed between the antenna elements. So this is how you put them together. Then if these bases go even smaller, you can have put more elements per antenna per square meter or per area if you want, right? So that's actually going really the right direction. What's not helping here is that your heat problem increases the moment, right? You put even more electronics on an even denser space. But that is where, companies like us at Texas will keep working to help on that area. Another positive trend in the satellite technology is that the cost of launch per the kilogram per weight keeps this decreasing. So this is where we have multiple new players now that help bring down the cost in these newer rockets and launches. And that enables then even more satellite players, more applications, services, business models there. And maybe look at an example like cell phones. Of course, they're directly connected to satellites already today. We can do voice, we can do text, but moving forward, we will have true broadband internet access over satellites from our cell phones. So in every area on Earth, you can really reach your broadband connectivity. And so we see there is a continuous growth and development in this market ahead of us. That means that our customers need to redevelop, but they also want to reuse things. They want to standardize components so they don't always have to start from scratch. They can really have an evolution in their product development. And there's also the need for one development and support multiple mission profiles. As Adrian had pointed out, you have the SEP for the LEO missions, the QMLP for the GEO missions, moving forward, you have that pin compatibility. And all that in mind, this is where TI is so convinced what's needed here is really space grade catalog products in a way you know what they are. You can reorder when you want them. You can reorder as many as you want. And you can do this also in 10 or 15 years from now.
Fantastic. That makes sense as an approach to the industry. I think we've seen how these kind of approaches obviously work in other industry sectors, and I think TI is really doing a great job of operating in this manner. And it was great to understand your thinking behind how this area is moving forward. So I think this is a great place to wrap up today's conversation. Thank you both for sharing. Thank you, Adrian and Michael, for sharing so many of your insights today on how phased array antennas work, what they're used for, the advantages that they bring, how to cope with the trade-offs in terms of the power and the heat and the engineering complexity, and what can be done to ease that integration and of such technologies into existing designs and space missions and plans for the future. So thank you both very much. We'll share, and to the listeners, we'll share more information on the products and resources mentioned by the guests today in the show notes. And you can find out more about TI on their website and on their satsearch portfolio, which is very extensive and has a lot of information on the products that we've discussed today. So thank you to everybody out there for spending time with us today on the Space Industry Podcast. We really appreciate your attention. If you like the show, please give us an honest rating and review on your favorite podcast player, and stay tuned for the next episode of the show when we will be speaking to more of the companies taking us all into orbit. Thank you very much.
Thank you for listening to this episode of The Space Industry by satsearch. I hope you enjoyed today's story about one of the companies taking us into orbit. We'll be back soon with more in-depth behind-the-scenes insights from private space businesses. In the meantime, you can go to satsearch.com for more information on the space industry today, or find us on social media if you have any questions or comments. To stay up to date, please subscribe to our weekly newsletter, and you can also get each podcast on demand on iTunes, Spotify, the Google Play Store, or whichever podcast service you typically use.